A very nice welcome to the Bhartiya Kisan Quantum Physics. And today again we are going to talk about Bohr correspondence principles. So let's start. You know, Bhartiya all Krishaks are quantum mechanists, or you may say them quantum physicists. And you foreigner, you don't know anything about physics. Only Bhartiya Krishaks know about all things about the physics. So let us start.
Bohr postulates for atomic model. The classical crisis with the model of the atom was not dissimilar to the case of black body radiation. Ernest Rutherford had proposed the nuclear model of an atom based on his discovery of the atomic nucleus. The electrons in this model were supposed to revolve around the nucleus, but then they must radiate and lose energy and eventually spiral into the nucleus. A classical nuclear atom turned out to be unstable. In 1913, Niels Bohr proposed an atomic model which accounted for the stability of the atom by injecting quantum ideas into Rutherford's theory. The model also proved highly successful for explaining the spectrum of the hydrogen atom. Bohr's atomic model was based on the following four postulates, three of which were radically different from the earlier models. First, electron in an atom moves in a circular orbit about the nucleus with the centripetal force applied by the Coulomb attraction between the electrons and the nucleus. Second, of the infinite number of possible circular orbits, only those are allowed for which the value of the orbital angular momentum mode of L vector of the electron is an integral multiple of h vector 2 pi. H by 2 pi. Here you see that Bohr preferred quantization of angular momentum instead of energy as was done by Planck in order to introduce h, the quantum of action, in his theory. Third, an electron moving in an allowed orbit does not radiate any energy. These states of constant energy are called stationary states. Note that the electron is not stationary in a stationary state. Fourth, energy is emitted or absorbed from an atom only when its electron jumps from one allowed orbit of energy EI E sub I to another allowed orbit of energy E sub F. The frequency of the emitted or absorbed radiation is given by Einstein frequency condition. H nu equals to cap E sub I minus cap E sub F. For emission, cap E sub I greater than capital E sub F. Now H nu equals to capital E sub F minus capital E sub I. For absorption, capital E sub I less than capital E sub F. Here we appreciate that the above four postulates are hybrid of classical and non-classical physics. For example, the first postulate is in accordance with classical physics, while the fourth postulates use quantum ideas. The postulates of the quantization of the angular momentum and the stationary states are also non-classical. The first postulate yields the following result for the nth allowed orbit. M Vn square by Rn equals to Z E square by 4 pi epsilon sub naught Rn square. While M is the mass of the electron, Z is the charge of the nucleus, and the electron is moving with a speed v, and in the nth allowed orbit of radius S again. The second postulate yields n equals to nh by 2 pi l cap. N equals to 1, 2, 3. L sub n equals to m v sub n r sub n. Since v sub n perpendicular to r sub n for a circular orbit. Here cap L capital is a cap of L capital is a unit vector perpendicular to the plane of the orbit. Thus we have m v sub n r sub n equals to n into h cut, where h cut equals to h by 2 pi and n equals to 1, 2, 3 dash dash dash. And we get Vn equals to z into e square by 2 epsilon sub naught 1 by n into h, and r sub n equals to n square h square epsilon naught divided by z e square m into pi. The total energy of the electron is the sum of kinetic energy T sub n and the potential energy U sub n. Here for the nth stationary orbit, so E sub n equals to 1 by 2 m square of Vn V sub n minus Jd square by 4 pi epsilon naught R sub n. Putting the value of V sub n and R sub n from above equation, we may write E sub n equals to minus of Z square e to the power 4 into m divided by 8 epsilon naught square h square into 1 by n square, or E sub n equals to minus of r sub infinity z square by n square, where r sub infinity equals to m e to the power 4 by 8 epsilon naught square h square. Thus E sub n proportional to n to the power minus 2. The suffix infinity on R appears because the mass of the proton has been assumed to be infinity. Putting the standard values of m, e, epsilon naught and h in a equation, we obtain the value of R equals to 2.18 into 10 to the power minus 18 और 13.6 इलेक्ट्रॉन वोल्ट जूल और इतना इलेक्ट्रॉन वोल्ट. According to Bohr's fourth postulate, the frequency nu sub mn of the emitted observed radiation when the electron jumps from the nth state to mth state is given by V sub mn equals to r sub infinity z square by h open bracket 1 by m square minus 1 by n square close bracket. This agrees remarkably with the frequency spectrum of the hydrogen atom. Immediately after Bohr's atomic theory was published, Frank and Hertz performed experiments which demonstrated the existence of discrete energy. However radical these ideas were, you can notice that there was still an attempt to retain a link with the classical physics. We know that at a high temperature or at low frequencies, the black body radiation formula given by Planck reduces to the classical Rayleigh-Jeans formula. Based on these ideas, Bohr in 1923 gave the correspondence principle. So let's know the Bohr's correspondence principle. The idea underlying this principle is as follows. The principles of quantum physics must yield the same result as those of classical physics in situations for which classical physics is valid, according to the correspondence principle. First, quantum theory should give the same results for the behavior of any physical system as classical physics, in the limit in which the quantum numbers specifying the state of the system becomes very large. Second, a selection rule holds true over the entire range of the quantum number concerned. Hence, at large quantum number, if any selection rule is required to obtain correspondence between classical and quantum physics, then the same selection rule holds at low quantum numbers also. To sum up the discussion so far, recall that Planck introduced a non-classical postulate to explain the black body spectrum, which was further extended by Einstein. According to this postulate, the energy state of a simple harmonic oscillator of frequency nu or discrete, and the energy of the nth discrete state is equal to nh nu, where n is a positive integer and h is a universal constant called the Planck's constant. Einstein regarded the quantum of energy as a particle. The quantum of electromagnetic wave is known as photon. As you know, this is a particle of zero rest mass, which always travels with the velocity of light and carries a momentum h nu by c. Einstein explained the photoelectric effect by regarding the phenomenon as a collision between a photon of energy h nu and the weakly bound metallic electron, in which a photon is completely absorbed and gives its whole energy to the electron, which may escape from the metal. You have also read about Bohr's atomic model, according to which electron in an atom move around the nucleus in a certain allowed orbit. In this orbit, energy is conserved, and angular momentum of the electron is an integral multiple of h by 2 pi. An atom emits or absorbs radiations only when its electron jumps from one allowed orbit to another. His theory proved highly successful in explaining the discrete frequency spectrum of the hydrogen atom. Thus, a new physics was born, which is known as cold quantum theory. This was further developed by de Broglie, Heisenberg, and Schrödinger into a new mechanics, now known as quantum mechanics. So let's study one of the basic concepts which forms the foundation of quantum mechanics, namely the de Broglie hypothesis, which led to the wave quality.
So here was a discussion of quantum physics, Bohr correspondence principle by Bhartiye quantum kisan krisak, and you foreigners, you are a very foolish. You don't know every Bhartiye kisan and krisak is a quantum physicist.